In this video, I introduce predicting videos with a hierarchical vector quantization variational autoencoder. VQ-VAE encoder E maps image X into latent variables ZE in the low-dimensional space, which is then projected onto a codebook E with key categories and D dimensionalities. And the quantization ZQ in the codebook is fed to the decoder D where nearest neighbor mapping as shown here. The gradient of ZQ approximates the gradient of ZE during backpropagation as shown here. This is input image X, and this is a reconstruction. This is encoder E, and this is decoder D. This is ZE in the latent space, and this is quantization ZQ. This codebook. The decoder D reconstructs the input image X from ZQ as shown here. The total loss function is defined as L, which includes three terms, namely reconstruction loss, codebook loss, and commitment loss. We combine these two terms to update ZE and E in two directions. Whereas G is a stop gradient operator, and beta balances the commitment loss. The codebook loss can be replaced by learning the codebook E via exponential moving average of previous values during training, as shown here and in this figure, where gamma is a decay vector and NIT is the number of vectors in ZQ in the mini batch that will map to EI. A likelihood-based autoregressive model optimizes the joint probability P as shown here. This is X smaller than I, indicates the dependence of the current pixel. This left pixels, this previous regions, and this the information at the previous frame. The video generative model consists of two main components, namely the first module compresses video into a discrete latent representation using our hierarchical VQ-VAE. And the second module predicts the joint probability from the quantized latent in autoregressive manner as shown here. This is a compression module, and this is a generative module. More details shown here. The model uses a VQ-VAE to compress video in a hierarchical fashion so that the multi-stage composition of a latent representation allows decomposition of high-level information from the low-level details. The top prior model is a pixel CNN with multi-head self-attention layers, where the multi-head self-attention is applied to compute the relationship between latent variables in the top layer. The bottom prior model containing local information is simply a 2D pixel CNN that generates frame by frame, as shown here. This top prior model and this bottom prior model. Prior is knowledge about what distribution the input video should be compressed into, for example, Gaussian distribution. Top prior means what information, for example, categories of objects, degrees of freedom in robots in latent space is suitable for video generation. For more details, please check with these references. Thank you. Bye.